So given Chris's just rousing endorsement of the current state of tools, I think it's natural that we now transition to discussing tools, and the poor guy to take all that flack is Byron Changuion. Changuion. Not Changuion, as I learned in school, but okay. So Byron is the engineering lead for the machine learning and optimization group at Microsoft Research in Redmond, Washington. He's currently focused on bringing the power of AI and new ML technologies to small, resource-constrained devices. That sounds really good for us. His team is responsible for building the embedded learning library, which we're going to hear about now.
Yes. Thank you. All right. Thanks, Kurt. All right. Hi, everyone. Thanks for coming to this conference, and thanks to Yevgeny in particular for inviting us to speak here. So I'm going to talk a little bit about the embedded learning library. We don't have a whole lot of time to cover everything, so we'll cover a little bit about what it is, and then we'll cover a little bit about what we're going to be doing next, and maybe take a look at how we measure success. So the embedded learning library is a cross-compiler for AI pipelines, specialized for resource-constrained target platforms. So that's a lot to say. What does it actually mean? So the AI pipeline that we're talking about could just be a model that you trained in PyTorch or TensorFlow, described by an Onyx file. You then want to run it through our cross-compiler. That means that the compiler itself is running on a more powerful device, your laptop, a desktop, whatever, but it spits out your machine code for your target device. And that's what gets deployed. It's also capable of doing data-driven lossy compression as well. And then, as I said, it's all about getting onto a very, very small device. So even though you might run the embedded learning library on a big device, at the end of the day, what comes out of it is machine code that is geared towards running on your small device. So the embedded learning library, which I'll often refer to affectionately as ELL, has been created at Microsoft Research, has been there for over 3 years. All the source code is out on GitHub. It has been since the beginning. We've been working in the space before EdgeML was the cool new buzzword. So there's a lot of good work in there. We also have a dedicated team of engineers and researchers who work on it. And in addition, we collaborate with other researchers around the company, and we ship some of the new algorithms, like, for example, Proton and Bonsai, which are really relevant to the small devices, and then use ELL as a ship vehicle to get it out into the world. So out on GitHub, there's the set of tools where you can compile, optimize, compress your neural networks or machine learned models. We also have a set of tutorials which showcase how you would deploy these models onto a set of very common hardware. And in the makerspace, it's often a Raspberry Pi or a microcontroller like Microbit or something like that. So we have tutorials that are focused on that. We also have a model gallery. The gallery is a set of pre-trained models that makers in particular can just use off the shelf and then deploy it to try and solve some computer vision or audio problem that they have. Our focus is mainly on CPUs because in the embedded space, you don't have all these extra pieces of hardware. And even in the case where you have embedded GPUs, the embedded GPU might already be fully occupied, driving a display and so on. So the GPU acceleration is very secondary. Our primary focus is definitely on CPUs. And in the makerspace, ARM is very, very popular. And while ELL is a general purpose compiler toolchain for all of these models, we do choose to showcase 2 areas. And you heard basically these 2 areas just pop up over and over again today. That's computer vision and it's audio. And audio, specifically the keyword spotting, which you can get to fit on really, really small devices. And then for computer vision, the Raspberry Pi is pretty popular for most people. So we showcase that, but we focus on computer vision models that can run even on smaller devices. Okay, so I won't spend too much time on the architecture, but as you can see from the components, you start with some pre-trained model, whatever your favorite framework is, and then we have a set of importers that can take that and turn it into some computational graphs that we understand. The alternative is you give us a data set and you run one of our trainers, and we will also spit out a model as well. For example, Proton and Bonsai are good examples of non-neural network-like models. So the important part there is that there's an optimizer that works on the computation graph. And what it has is a set of, let's say, switches and knobs and dials that are exposed by a platform abstraction layer. And together with a target profile that was generated from whatever target you're trying to deploy to, the optimizer can make the appropriate choice given the combination of the computation graph and the target profile of what code it wants to emit. So in this case, LLVM is up there because we use LLVM to emit a lot of CPU code. There's OpenCL emitter, let's say, for the GPU. At the bottom, there's our set of dependencies. There's LLVM, there's OpenCL if you're going to use the GPU. There's also BLAS if you have a BLAS library on your platform. If you're Intel, MKL, OpenBLAS on the Raspberry Pi, for example, or you don't actually have to use it at all, and we will just generate code for you. Okay, so most of the cool kids are building AI runtime, so why did we build a compiler? Well, it's a little bit like asking, benefits and drawbacks of interpreted code versus native code. They're both perfectly good. It all depends on what you're trying to achieve and what you're optimizing for. So let's say in AI runtime, you want portability. When you have a model that you want to run on a bunch of different heterogeneous hardware, let's say mobile phones, for example, you already have a nice disparate set of OSs, but you have a framework that can run pretty much anywhere. You just want to keep pushing updates to the model, and it's a lot harder to update binaries in the store, for example. So, in this case, a runtime is a great option. The other one is just seamless integration from, or migration, I should say, from the edge to the cloud and so on, especially when you have pipelines that you're updating all the time. You have a model you're trying to train, deploy, and then sort of refine, right? Why would we choose a compiler? Well, here you can do very model-specific optimizations. For example, if you see a bunch of nodes that just have a bunch of linear operations, you can just fuse linear operations together. You can do things like choosing different convolutional methods based on what follows or precedes that node in the computation graph. The next thing is there's target-specific optimizations, like I know what kind of SIMD instruction support you have. Do you have floating point? What is your L1 cache size? All of these things affect the type of code I might emit, which is not possible really with a runtime that's a lot more general. And then lastly, since we're talking about the embedded space, space is obviously a big thing. If you don't have enough space to fit these large models, like runtimes don't really help you there. But when you have a compiler, you can just generate the code for only the operations that you're actually using. And so you can reduce the amount of code that gets put onto the device. And so therefore, you can squeeze more in there. And then perhaps the best of both worlds would be a sort of just-in-time compiler. That's not what we're working on yet, maybe in the future. But we think that would sort of span both of those pretty nicely. Okay, so let's talk about how we evaluate models. So ELL is used to basically take in these models and runs a set of optimizations. How do we know whether we're doing well or not? Well, so generally speaking, there's this notion that you can sacrifice some small loss in accuracy for some massive gain in whatever your cost is. So, people use a number of compression techniques. We've heard, a few already. So things like more efficient architectures. Hey, choose a ResNet or a MobileNet versus a giant VGG that everyone keeps using as a standard model, right? Other things you could do is train a really large model and then prune it down along the way. Whether that's in training or post-training, it's totally fine. But all of these things in the literature, they're all great ideas, but what they do is they give you sort of two independent values. Hey, when I ran this technique to compress it, what I found is I dropped 5% in accuracy and I made it 3 times faster. Hey, this is great, but how do I know that that is a cost accuracy trade-off that's worth making, right? I don't actually know, because how does that compare to the whole suite of models that already exists out there. Is it better or worse? I don't really know how to compare them. So I think we're going to just quickly take a look at doing an architecture search to get these better models, but we have to first address this notion of evaluation. So let's look at some graphs that we have that show some of the models that we had back in January 2018, but we're going to use this lens that we just said about the cost-accuracy trade-off, right? So first we define our y-axis. We decided this is an image classifier. We have top one accuracy. We picked a standard data set, a realistic data set. So this is ImageNet. On the x-axis here, we picked our cost. You can pick whatever cost you want, and you should pick it for your scenario. It could be energy usage. It could be space or memory footprint. In this case, we chose speed because that's a very common one that people care about. And we define speed to be how many milliseconds does it take to push one frame through the entire network. Okay, and then lastly, you got to pick your benchmark hardware and keep that the same for everything. So in this case, it's a Raspberry Pi 3 running at 700 megahertz. So every point you see on the plot here now has two axes. It's a different model. You can tell by the arrow that says model. So, you know, in a very naive way, you can see that the model that is, or the point that's just below where the arrow says model is obviously not a good model as compared to the one above it, because for the same cost, this one is more accurate. And of course, in general terms, everything that forms the top left edge is going to be more optimal, and that is our Pareto frontier. We heard that word already today. And basically, we're going to define Pareto, our success in terms of the Pareto optimality. So a model that is on the curve or defines a new point in the curve is optimal. Anything that's below it is not optimal. And I know that we're making progress, or a technique works well when it moves the curve. If it doesn't move the curve, you have not moved state of the art. All right, all you've done is you've made some changes, which might be good for a scenario, but it's not state of the art. So here's as an example that we did. We took some model. In this particular case, when we binarized it, it just ended up over here on the graph. And you could see that this might be a perfectly good model for certain situations, but it's certainly not state of the art. Why? In terms of the cost accuracy trade-off, it's not a good trade-off. I could do a little bit more cost and get a big bump in accuracy, or I could reduce my accuracy a little bit and get a really big cost savings by moving to the left. There's those other 2 points above and to the left of it. So in that case, this is how we know, all right, we have a standard way to compare models and techniques, and how did we do? So this is what we use as a scorecard on the team. This was January 2018. Here's February. Oh, we got one lone guy breaking through the frontier. So progress. This is great. All right. March. All right, we're doing better. Now we've got a whole suite of new models coming in. That's pretty good. You can see that the accuracy is getting better and the cost is getting slightly less. Lastly, you know, here we are in April, and we've got lots of new points, and they're definitely way higher accuracy and definitely have decreased the cost for that accuracy, which is really nice. So this is what we use to basically standardize across all of our techniques that we use in our compiler or new models that we try and create. How are we doing relative to what's out there already? If it's not optimal here, we haven't pushed state of the art. We might have done something useful, but it's not our state of the art, and we're trying to push state of the art. So architecture search is one way that we can do acceleration, right? You can come up with new architectures, and you get this cost accuracy trade-off, and that's pretty good. There's another type of thing that you can do, which is to accelerate models you already have, right? And those fall into two buckets. There's the lossless acceleration, and then, of course, there's the lossy acceleration. So let's look at lossless acceleration. Remember, I said we're building a compiler. So when you think about it, there's a variety of things that we could do. I'm going to describe a few of them for you. Since the graph that I showed you is about image classifiers, you know that we're spending most of our time on the convolutional kernels. And so there's a variety of techniques, lots of different ways of building convolutional kernels. You could do unrolled techniques, you can do Winograd, and so on. You could do direct convolution. There's just a ton of different varieties that you could do. Next, you could modify scheduling, right? It's an ARM Cortex A53, so therefore it has 4 cores. How you do parallelization, what you choose to parallelize, that can have an effect on the cost. There's also engineering, like, all right, we know that we have this set of neon instructions. How do we actually emit code that takes advantage of all of this stuff? And what you should see with this is that by making compiler adjustments, you can not affect accuracy at all, and all of your models should just move to the left, right? So let's see how we actually did. So that's what we invested in a bit in December, and then January and February. So we start here in January of this year. So February, you could see that some of the models did do the Cupid shuffle to the left, which is good. I'll just point out one at the very top because it's the easiest to see. You can see that the very top one there was almost at 1 second. That's our cutoff point. Any models that take more than 1 second, we're not interested in. And hey, it shifted. It's now like just over 800 milliseconds. That's pretty good. And in fact, there's other models that did the same thing. If we go to March, you can see that that same model is now, we just decreased, we took off 30% of the cost. Its accuracy stayed exactly the same. And if you follow down on other points, there's a whole bunch of them that did exactly the same thing. They just moved to the left. Okay. One last thing I want to point out is the dot at the top right. It's not a mistake. That model is not a new model. That actually was an old model that was totally irrelevant. It was outside of our cost radius. But by applying a new compilation technique, you just run it through our compiler, and suddenly this irrelevant model became relevant again. All right, and so it met our cost accuracy curve, not just to become relevant, but actually to become Pareto optimal given its accuracy. So the cost accuracy trade-off there made it state of the art for that model. Okay, so that is lossless acceleration. Let's talk a little bit about lossy acceleration. In the literature, you'll find that it's often the case you'll get a really large network like VGG. It's very over-parameterized and so on. You apply some technique, you apply it uniformly throughout the whole network, and then you get some result. But in reality, most of us actually start with models that are much smaller. They're not that over-parameterized. You've already done things to reduce the number of filters, reduce the number of layers, and so on and so on. So really, you might find that you might want to mix and match techniques instead. For example, hey, take your ResNet that you've already made smaller, and you apply depth-wise separable layers to it instead. And then on top of that, you either binarize or quantize the pointwise convolutions, which is where you're spending most of your time, right? So you can mix and match techniques, but they, of course, these are all lossy, right? You're going to pay some sort of drop in accuracy, but hopefully you'll get a big payoff in the cost. All right, then we have this notion that, there's two things pulling against each other. One is whatever technique you apply, you want to make sure the accuracy is as high as possible, but you want to pay as little as possible, which kind of pulls you in the opposite direction, right? So as we heard earlier today, this notion of co-engineering or co-design, both the engineering and the ML is quite important. We want to start with things we know how to execute really well, and then we want to be able to train or design the networks that we can train that take advantage of those things and go back and forth between them. And you can do this during training. You can do it with post-processing as well. Doesn't really matter. So in this case, I'm going to walk you through an example that we just did. It's just one example. We do many versions of this. So let's take quantization. Quantization is very, very promising. So when is 0 not a 0? Oh, easy, when it's a -1, right? Because in binary, you have the semantic choice where 0 and 1 could be 0 and 1, or mathematically, I could treat it as a -1 or 1. binarized networks do this, and you have to make this choice. Semantically, what do your bits mean? Ternary is another example here, where in 2 bits, I could just be, -1, 0, 1. Then we have, lookups based on whatever the quantized value is. The lookups values themselves could be anything. We have iterative sum, where each of the bits actually represents a different floating point number, which in combination will give you an actual approximation of a true floating point at the end. And then there's, linear and exponential and so on. Now, the choice of semantics basically dictates how many operations you're going to need to be able to do a dot product and get your result at the end. So you have this giant choice of things, and you got to keep that in your head. Another choice you need to make is the quantization representation, right? You could pack all the bits next to each other. So in other words, least significant to most significant, or the other way around, doesn't matter, but then followed by the next value in the same order. Or you could do bit planes, where you pack them in like sardines. You have all the, let's say, least significant bits followed by the next most significant, and so on until there. And that means your values are actually in these lines and planes, but they don't have to be contiguous at all, right? It's just a semantic. So let's walk through an example over here. Remember, you have a giant set of choices. You might have to try all of these combinations. In this particular case, we tried ternary weights. There's 3-bit unsigned linear activations, and it's in bit plane format. I'm not sure what's happening with the coloring. It wasn't in my slide, but we're going to continue. So what we're trying to do here is we're trying to get, at the end of the day, a dot product, right? So we have 2 vectors there. One's weights. One is your activations that you're then going to do dot product. And like a street magician, I'm going to tell you, hey, when you do that dot product at the bottom there, remember the number 7? That's your card, all right? Everyone remember number 7. So when you pack it in bit plane format over here, this is basically what you end up with. I won't spend too much time in the details. But a good thing to remember is your activations are now these numbers. But the weights, since they were just 2-bit, they were ternary, one is actually magnitude and the other one is sign. And that means that we can take advantage of that, right? OK, so now what we have is just, we do the sum and so on. And at the end of the day, well, after you've done all of these things together, you're going to get this magic number at the bottom there, which we said was -7. And is that your sign? Yeah, I'm sorry, is that your card? Yes, it is your card. It's -7. So we did some math here just in bits, but we actually got real numbers out. And that's the promise of quantization, that this is actually going to work out better for you because you traded some precision for more operations. OK, in this case, the number of operations, if we do back of the envelope calculations, we'll end up with about 3 instructions if you do 8 bits. And that's not good, because with 8 values here in floating point, I could just do it in 1 instruction per floating point. However, we take advantage of the neon instruction set, then we can see that actually we're only paying 0.2 instructions. That's 5 times faster. OK, so we can see the actual performance speed up over here that we got at the end of the day. It does match what we have. That's the engineering part. Can we train networks that take advantage of this? Yes, we can. Ternary weights or trinarized networks, you can see that they're more accurate than the binary counterparts. This is the model on the very left. You can see that at 0.8, which means 80% of its full precision cousin is what we ended up with binary. And then lastly, we need to quantize the activations. The activations can be quantized with n number of bits. And you can see that with the trinary networks, what we end up with is better performing than the binary networks. And it gets up to 96% accuracy compared to the full precision network. All right, so that's basically sort of what we did. If you want to see what the results of that are, you're going to have to stay tuned and look at our gallery to see what we ended up with. I think that's all we have time for. All right, thank you very much.
Let's take one question.
Yeah.
So I had a question, and actually I tried to communicate it last night. I guess it didn't get through. But you showed us a lot of architectural search, but you didn't give us any sense of the family of architectures that you're searching over. Can you just say a little bit in terms of number of layers, the size, number of model parameters, and so forth?
Sure, they're all different. They're all
they can't be that different.
Yeah. So we started with darknets because at the time darknets were the most performant. But mostly what's ended up being...
Particularly if you're in Seattle.
Particularly in Seattle, yeah. But if you're... but mostly what's relevant right now are just very custom ResNets. And of course, we're exploring a bunch of other architectures, dense nets and mobile nets and so on. But most of them are ResNets that have taken ideas from mobile nets and exception nets. So for example, applying depth-wise separable filters and so on. So there's not actually, most of them don't have a classical structure from what you see in the papers. It's a little bit of a mix.
Okay, thank you. All right, great.
Okay.
Great job.